Hey everyone, welcome to the fourth lecture in our series on imitation learning. I'm Sanjivan Chaudhary, a research scientist at Aurora and soon to be assistant professor at Cornell. Today, we'll talk about what robots can learn from intervention. We'll see that intervention fundamentally reduces to two bits of information. When did the human take over, and when did they return back control? A key insight is from just these two bits, we can discover a lot about the value function of the human. So let's begin by returning to our running example of building a self-driving race car that learns via imitation learning. So if you remember, we have a human driver that's driving round and round the track, providing multiple demonstrations of how to drive. So these are sequences of states and actions. However, when we train a learner via behavior cloning, we see that this learned policy cannot stay on the track. We saw that when this learner makes a single mistake, it goes into new states where it continues to make mistakes. In other words, behavior cloning compounds and incurs an OT square epsilon error. Fortunately, we have a solution, Dagger, that interactively queries the experts on all the states the learner visits, and then gets labels from the expert and aggregates these labels to train a new learner that eventually learns to stay on the track. As we saw, Dagger does not suffer from this compounding error. In fact, it achieves the best possible rate, the optimal rate of OT epsilon. Now, while this seems great in theory, there seems to be something unsettling about what we are asking from the human. Put yourself in the race car driver's shoes. We are asking you to label states that the robot visits that may be far off the track. These are states that you, the human driver, would likely never visit. And it seems unreasonable to ask the human to label all of these states. This seems unsafe, it seems impractical, and approaches like this simply cannot scale when working with real humans. So are there better alternatives than the human labeling every state the robot visits? We argue the answer is yes, in which humans teach and learn. So let's take a look at our race car example again. Instead, can we learn from a much more natural way? At this point, a human driver intervenes. They take over control and drive the robot back onto the track. They then return control back to the robot until it goes off the track again. And this process continues until eventually the robot learns to perform the tasks. So how can we use this intervention information to learn the right behavior? Instead, is there a more natural way that we can learn? Yeah. So recall that data here is a sequence of state action pairs. Here states are the intervention states, actions are demonstrated recovery actions, and you train a policy on this data. Now, it's fairly obvious what will go wrong. First, you're training the policy only on the learned latest recovery behavior. So it not only it forgets the original nominal driving as well as prior recovery. So this turns out to be a terrible idea. Slightly better option is to aggregate intervention with the original demonstrations. Instead, can we learn from a more natural way? For example, can we learn from interventions? Interventions are a very natural way that humans teach and learn actions executed by the human. You train the first policy on this data, and you proceed iteratively, where at every iteration you roll out the learner and collect intervention data, which is a sequence of state action pairs. Now, the state distribution here is a bit tricky. Part of it is when the expert is in control, but notice this is not the distribution of states the expert would have visited on their own. That initial distribution is coming from when the learner is in control. And so the state distribution is a composition of these two probabilities. Learner being in control and leaving the track, and then the expert taking over. So you're getting states from this sort of composed distribution. Then actions are simply the actions the expert would have chosen in these states. We then aggregate this data with the original data set, and we train a new policy on this data. Now, why does this work? If you recall from our previous lecture, this is nothing but follow the leader algorithm that we know has a no regret property, which means as the number of iterations n increases, the policy does as well as the best expert in hindsight, access to all the data up front, which means as the number of iteration n increases, interestingly, this approach runs into a problem. It results in the wrong learning incentive. To see why, consider a simple example of a straight line track. Here, every time the robot leaves the track, the human takes over and drives the robot back onto the track. Let's ask a simple fundamental question. What is the best policy in hindsight as n tends to infinity? Which means, let's say we can drive regret precisely to zero. In some sense, this is the best AG Dagger can hope to achieve. To see what this policy looks like, let's take a peek inside the mind of the learner. Let's also assume we've been running for many iterations, so most of our data is intervention data. And on this data, we have driven error to less than epsilon. We see that the policy perfectly imitates a human off the track. So imitation loss is 0 whenever the policy is off the track. But on the track, the policy may not imitate the human well because it's just not represented in the data set. And so it imitates the human pretty poorly on the track. So what happens when we execute the learner? We see something strange. We see it veer off the track and then perfectly recover and come back on. In some sense, this sort of behavior is a reflection of the loss function, which incentivizes the learner to perfectly recover, but does not incentivize the learner to stay on the track. Let's try to formalize this phenomenon. So pi star here is the best policy in hindsight on the cumulative loss. Notice that the distribution of states in this loss function is coming from the distribution of intervention states. So the learner is perfectly imitating the expert on intervention states, but this is not the same as the distribution of states encountered by the learner. And so you get mismatch in incentives. The learner is incentivized to do well in the distribution of intervention states, but not on the distribution of states it encounters. This leads to our key insight. We shouldn't just be using intervention explicitly, but instead realize that interventions are laden with implicit information about what the expert wants, which we fail to exploit. So if you look at our race car example, if you roll out the learner and the expert doesn't intervene, what can we say about this sequence of state actions? Well, we can at least say that the robot is in good enough states that the human feels comfortable to let it continue driving. Even though it may be making mistakes, it may not be doing exactly what the human would like it to do. Still not bad enough for the human to intervene. However, if the human does intervene, what can we say about those particular states? Well, we can say that at the point of intervention, the robot has entered a bad state that's deemed unacceptable to the human, maybe because it made a series of mistakes and got off track. And we need a loss function that essentially captures this sort of ordinal information, that there's a set of states that are good, that are preferred to a set of states that are bad. So far we've been dealing with one type of loss function that just says do good actions. We need to add a second type of loss function that says don't do bad actions that cause you to go from a good state to a bad state. Let's try to formalize this intuition within the familiar framework of an MDP. So recall that an MDP, or Markov decision process, is a tuple of state, actions, transition probability, and costs, where costs are unknown in the mind of the human. A policy pi is a mapping from states to distribution over actions, and policy pi h is the human policy that is optimal. You can also define the action value function of a policy. So q pi stat is equal to cstat, this is the one-step cost of executing action at state s, plus the value of executing pi from the next state onwards. So st plus 1 is the next state, and at plus 1 is drawn from pi. This second term is also known as the value of pi from state st plus 1. We use the symbol v to denote this value. Okay, so let's look at a diagram to get some better intuition. So we have a race car that at a particular state executes an action. You then use policy pi to drive the robot all the way to the goal. You can then ask the question, what is q pi stat? Well, it's the one-step cost of executing at st plus the value of the future state on executing pi. And for this particular example, both of these terms are small. The one-step cost is small, you're basically driving straight. And the second term is small because the policy pi can nicely drive all the way to the goal. Now let's take another example where the race car is slightly at an angle about to go off the track. Here the value is high, not only just because maybe the one-step cost isn't that high, but the future value of pi is really high because it spends a lot of time outside of the track incurring a high cost. Let's take a look at the contours of the value function v pi s. Notice that the value function grows much more sharply if you move laterally off the goal than if you move longitudinally off the goal. This is reflected of the nature of the cost, because the agent incurs a high cost when they're laterally off the goal, when they're off the track. The value function v pi also tells us how an agent approaches the goal, essentially by traveling perpendicularly to the contours of the value function. Right? So when you're on the track, you're driving straight to the goal, but when you're off the track, you're taking sharp curves to reach the goal. Okay, so now that we have built some intuition about value function, let's take a journey through the various levels, and we'll see how this is akin to a journey through various levels of the human value function. First, let's begin with the human fully in control. So when the human is driving, they're likely occupying low values. Let's call this level 1 of the value function. So a set of states that has the lowest possible value. More formally, the q value of these states, q pi h sa, is much smaller than epsilon t, an arbitrary threshold, where states s are drawn from the policy of human driving. Now let's assume that the robot's in control, and it likely strays off the path the human would have taken. However, the human does not intervene. Here we can say that the q values are below a threshold epsilon t. In other words, these state actions are good enough. And we can denote these state actions with a higher level of the value function, level 2. Now, if the robot leaves level 2, the human intervenes, takes over, and drives the robot back, right? So we can think of this set of states being in level 3. And we can definitively say that if the human's taken over, the q value of the state actions are more than the threshold epsilon t. And so these higher q values are denoted by a darker color to show that that's the highest possible level that the human can tolerate. But notice one interesting thing, that when the human is taken over, the actions they're demonstrating are locally optimal. So while the absolute q values are high, the relative q values of those demonstrated actions are cheaper than other alternatives. The human, in this case, drives the robot back into level 2 and returns control to the robot. And this process continues, where the robot stays in level 2, leaves, the human takes over, drives back. Now let's zoom in on that little bit of, on the intervention portion, and take a closer look at what's going on. So the robot's in control, and at some point you see the human take over and then return back control to the robot. Now there is a conundrum. These levels I sketched out are latent because the cost function is latent. As a result, we have no idea at what point the robot left level 2 and entered level 3, and we don't know when the human left level 3 and came back to level 2. But we can begin by making educated guesses. So we can say the first part of the trajectory is definitely level 2, as the human is not taking over. The human is letting the robot be in control. Similarly, we can say the last portion of the trajectory is also in level 2 because the human consciously returns back control. We can also extend by saying the portion just before human probably entered level 2, and so that's level 2. And then we can look at the part where the human intervened and say the part just after that must definitely be in level 3, right? So this process allows us to chunk an intervention segment into 2 clusters, level 2 or level 3. All right, so let's take a step back. Our key insight is that interventions tell us information about the human value function. So a simple question is, can we use interventions to infer the human value function QSA? And the answer is yes. We do so by proposing a method, expert intervention learning, which happens to be a very simple constraint optimization problem. So we are solving for a value function Q theta. The objective is simple. Take all the action labels that you get from the human, so this could be from human driving or from intervention data, and correctly classify the human actions. And since the classification objective is non-convex, you can come up with a convex upper bound like a hinge. Now we add a set of constraints, a set of inequality constraints that says the value of a set of level 1 plus level 2 states are less than the value of state actions belonging to level 3. And that's it. This is also a linear constraint, so the entire problem is convex, so use your favorite convex optimization to solve this problem. And so we implemented this idea in this paper in RSS 2020 and deployed it on a real robot and showed that you can, from very few interventions, you can learn to drive like a human driver. There's also a pretty straightforward probabilistic extension of our paper. So here you assume humans are noisy, so their policy pi is stochastic and proportional to x of the negative of the value function, right? So low values get chosen with high probability. Secondly, you can assume the level classifications are noisy, right? So there's an overlap between level 2 and level 3 states. And so in this probabilistic version, the basic idea is to maximize the likelihood of data. Now, it turns out that the data has 2 parts. The first part are the demonstrated human actions. And so this turns out into a standard cross-entropy loss. Plus, there is this sort of classification that turns out into a soft classification loss, where you take a soft min over all state actions belonging to level 3, and you say that must be more than the soft max of all state actions belonging to level 1 and 2. Minimize it using your favorite optimizer, and you end up getting your value function. This brings us to the end of the lecture. Let's recap the key challenge we tackled. That interventions are laden with implicit information. To exploit this information, one must reason in the space of human values. We learned that we can think about this problem as a clustering of 2 states. Good enough states where the value is low enough such that the human does not intervene, and bad states where the values are above a threshold that forces the human to intervene and bring the robot back down to lower values. And knowing this allows us to infer values by either ranking or probabilistic formulations. And looking ahead, a lot of open questions that we can ask. For example, is the intervention model we're using too simplistic? How would we model something like the trust? For example, we know that humans are always estimating what a robot might do and intervening based off of that. This makes the intervention model quite complicated, and creates a sort of interaction where the robot interacts with the human that has a mental picture of the robot. And so figuring out how to tractably solving such problems is an interesting open direction of future research. With that, we are at an end. Thank you for your time. Be well.